I can start? Is everybody? Okay. So let's start the last lecture of the afternoon. So the goal is to understand the Legendre transformation. The tangent bundle to the cotangent bundle using the Lagrangian L. So L is in the Lagrangian, so you're let me emphasize that word. So, the basic example is let V be a vector space here finite dimensional, of course. So let me just say finite dimensional. I think for me finite dimensional. Maybe we don't need that. And we start the infinite space. And we want to have a Legendre. What we want to have is Legendre of a function on V so the Legendre of the function on V is a function on V star. So from the motivation of the last lecture, you want to have some way of mapping velocity to momentum. That's physical language that is going on here. The Legendre of some function on V is a function on V star. Okay. So the way to think about this, my students all tell me I only have one picture, it's this. My only picture. If I have a fiber of the tangent bundle, say some base point here, A, I don't know, base point, I don't care, it's just maybe ABC, it doesn't matter, base point. No, some base point, okay. And this is the fiber over X. That's V. Okay. And we have some function on V. Have some function defined on V, on this fiber. And this Legendre, maybe I'll call this L, script L of F. Legendre will take the functions on the fibers to a function on the fibers. Here's x over here, and here's the cotangent element. Let's restart. And here's M. Now you're going to hate me because I'm going to change notation right in the middle of this. If we have a point in the base, the physics guys and the Arnold will refer to the coordinate here to the, and to the point and everything as Q. Okay. The physics guys and Arnold will refer to the things here as Q point. Okay, that is velocity. Okay. And the functional here, the function that you will be talking about here is P. Okay? Yes.
So Q point is 1 point in...
No. I'm glad you asked that. It means the variable of that fiber. Yeah. Yes.
Not section.
No, it's, for one thing, if you have a point,
It's just one
Well,
in the
well,
in that space.
you will see, it takes some getting used to, I'm terribly sorry. But if you will have coordinates Q down here, and Arnold will call these coordinate points Q, and he will call the coordinate points in the fiber, associated fiber, Q point. Okay? And you will have down here Q, because it's the same base. The base is not going to change on this thing, right? It's the manifold. So you will have coordinates here Q, and you will have momentum coordinates above that, which are called P. Okay? Okay? Yes.
So where is F in our picture? F is just in that...
F. I greatly appreciate all these questions because if I start writing everything, it gets crazy, right? F, I just said, what we're going to define this thing is on a vector space, just some stupid thing. But I'm going to define it here on the bundles fiber-wise. So I define on each fiber, and it'll be smoothly varying and so on. Okay? Is that okay, Maria? No, you're not okay with it. I'm going to talk about the Legendre transformation of a function on a vector space to a function on the dual space. But I'm going to apply it to a function on the tangent bundle, or coordinates on the tangent bundle, to the coordinates on the cotangent bundle. Okay?
So does that mean that F stays in that fiber?
F is on this fiber, but yeah, I'm going to transform it to a function which I will call H on the other fiber.
Okay.
So, and I call it H for Hamilton, because if you transform the Lagrangian of the Euler-Lagrange equation, you will get the Hamilton. Okay. It's a little bit confusing. I'm sorry I'm confusing, but I think it's confusing. Just keep that in mind, and let's start with a silly situation. The basic picture of Arnold. So I strongly recommend you take a look at the corresponding part of Arnold. It's this. This is the x-axis, so forget P and Q, but that x will be Q. This is the... And this is, if you like, a vector value of x, but maybe just one dimension, I don't care. And this is the y-axis, That's one dimension. And now, Arnauld takes a linear function. This is high school mathematics. Okay. Let's just do this in high school mathematics. Okay. Usually, if you understand high school mathematics well enough, you can do well in better math. This is a linear function. Y is a linear function of x. Okay. And unlike what I just wrote on the board with MV, and unlike what I wrote in high school when I write y equals mx, there's a reason for m being sloped, by the way. We will write here y equals px. Okay. Now, okay, so if you like, p is the slope of that line, but if you like even to be a little bit more careful, you think of this as being p of x, and you think of p as being a linear function. Okay? It is a linear function, right? When you write a line, y equals p times x, if you like, p times x means p1 times x1, p2 times x2, and so on, right? P is p of x. It's the linear functional p applied to the point x. Punkt. Okay?
But isn't P a linear functional on x?
Hmm?
Isn't P a linear functional on x?
This is, I understand you're thinking of the application, maybe, but this is just, think of it here. Okay? What he's saying, I'm going to say what he's saying. He's thinking ahead of us. I should really write P is a function of Q point. Right? Because Q point is the fiber variable over the point Q. Right? That's what you're thinking. But let's keep it simple with the notation. Okay? And now, this is another function which is nonlinear. This is the function y equals f of x. So, just some function of x. Okay? And the only assumption here is that f is convex. As you mentioned, f should be convex. So f is convex. Of course, I would like it to be smooth and so on. So in the one variable situation, its derivative, convex means its derivative is what? Positive, I think. The second derivative is positive. Right? That's what convex means. Second derivative. And now, interesting thing to do is to start taking tangents here to this curve, this convex curve. Tangent here, tangent here, tangent here, tangent here, tangent here. Oh, tangent there. And I did a bad job probably. But you all will agree that if f is convex, and I take all these tangents, there'll be precisely one line that is parallel to that line, right? So, there will be a point, x, here, which depends on P, where that line and this line are parallel, a unique point. And that point, if the convex function is smooth, varies smoothly with the convex with P. If I move the line smoothly, then this tangent line moves smoothly, and this point moves smoothly, everything moves smoothly. You can prove it. Okay. Then you want to have a function here, and the function here you take is this. So this length is the Legendre transform. You take a function which is convex, you take a linear function, you find the unique point where it's tangent, that defines the point x of p, and you take the difference of these points. Okay, that's the Legendre transform. Okay. Now we need to learn how to do that. Is that the way you do it in physics? I hope. Something like that. Okay. Well, how do we formulate that in terms of, I mean, that's just geometry to make us understand it. So first, always do the geometry to make us understand it, and then we do the analysis to do the computation. How is this point determined? Well, it's completely obvious that this length is maximized here. So that this length is determined, this is the maximal length of here. Now, everybody knows how to get the maximal length. It is using, of a function. The function is given to us, y equals p of x. We want to maximize that function, that difference, on this manifold. So what we want to maximize is this thing on, and now I'm going to probably make a mistake here, this manifold. So you use the usual Lagrange multiplier method to maximize this length on this manifold, right? On this condition. This is the condition. Y equals f of x is the condition. This is the Lagrange multiplier, and we're maximizing this guy, the y minus p of x. Right? There is no condition that this is called Lagrange multiplier, because I am sure this is the first application anybody thought of for Lagrange multiplier. Right? And now you need, you know, the theory of Lagrange multiplier means find the critical point of this function. Right? So let's do that. So critical points. Critical point or points of this thing. So we want to find critical points of that. So let's do it. We differentiate with respect to x and set equal to 0. We get p of x. Of course, p of x is p times x. And don't forget, this is now a function p times x. That means a vector function times x, right? So p1, x1, p2, x2, and so on. Okay. And we maximize that with respect to x, which is a vector function. And it says that I want to p, probably, I think I want plus sign.
making some mistake.
Okay, with respect to x, I get the derivative of x is minus p, and the derivative, minus, I do want plus. Yeah, I do want plus. Plus, I'm not sure I want plus. Lambda, partial f, with respect to x. Right? Right? That's gradient, really. Okay, that's that, so that has to be 0. And with respect to lambda, that's only a function of one variable, so that means, oh, that's good. But that's y minus f of x equals 0. And with respect to y, that's, okay, here we go, minus p of x plus lambda plus lambda, minus lambda f of x, right? No, with respect to what? No, plus lambda. I'm sorry.
Are you differentiating with respect to y? Yeah.
No. Yeah? Am I making a mistake?
We're differentiating with respect to y, correct?
Hmm?
So we're differentiating with respect to y.
Yeah, y is just one variable, so I'm,
You have it one.
I'm jumping around here. So I'm sorry. The derivative of with respect to y is 1 plus lambda, right? And the differentiated with respect to lambda is that. Okay, this says, what do I want lambda to be? I want lambda to be, I want to get the right sign here. Lambda is here minus 1 if it doesn't matter, Prof. Oh, it's okay. No, it's not okay.
Minus lambda, of course.
First equation in minus lambda times
So it looks to me I get a sign I don't like here.
So,
I think it's the first
with
equation with
first
respect to x.
differentiation, we have minus sign, minus lambda.
Because it was minus f of x, right?
Oh, maybe that's good. Yeah, maybe that's good. And lambda equals minus, I bring it over here, yes, and lambda equals minus 1, right? And so this will be, it'd be what I want, p equals df dx, right?
What was lambda? Lambda was what?
The Lagrange multiplier.
Lambda's.
I mean, this is this whole business of Lagrange multiplier, right? Lambda is a Lagrange multiplier. So this is the whole business of how to find a critical point of the restricted, right? And I think the signs are right now. I think we're now, well, I'm lucky. You guys are, okay. So, wait a minute. So, this minus sign is because I had a minus sign in front of the, of f. Right. And this, okay, everything's good. Okay. So, okay. So, what we get out of this is, you believe it. I mean, I just did the mathematics, but you believe it with the geometry. That P equals df dx. Well, it means that the gradient of the function of the nonlinear function is the same as the linear function, right? Which it has to be. I mean, that's what we learned. But this equation here is an implicit equation for P, for x of x equal x of P. Right? Regard that equation as an equation for this function x of P. Okay. Now, so let's get back to our, this is it. I mean, there's nothing more to do. Right? It's really simple, right? B equals, but it's highly non-trivial because of this implicit nature of this equation. Right? Okay. So we have now F is the Lagrangian on Q and Q point. Okay? Right? And these Q and Q point are coordinates of the tangent bundle that we're discussing. Okay? Okay? And P and Q and P are the coordinates of the cotangent bundle that we're discussing. Right? So the Legendre transformation is stupid in this formalism. It's Q, Q prime, and I'm getting to what I'm yes. I'm going to Q point goes to Q P. All right? So here, P is a function of, is Legendre of Q point. Right? Because it's fiberwise. Now do you get my picture here? Right? You have Q and Q point, and these are the coordinates here in this tangent bundle. You have Q and P, and these are the coordinates in the cotangent bundle. Legendre is a product. Legendre takes Q to Q and Q point to P. Now you're happy, right? QP is a function of Q point. Right? Okay. 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 And now the Lagrangian, the Legendre of the Lagrangian of L okay, here we go. This is the change. Wait a minute, I need to write this in a better way. No, I guess this is okay. This is the Legendre of L. Okay. What is the Legendre of L? It's this length here. Right? So it is P Q point. This is what you're looking for, I think. That's this point here. Maybe if I put this here, P, this is P Q point. Okay. And this thing here, what is this thing? This is the function this is the Lagrangian. So this is PQ minus L. Okay. Okay. I will write this for fun of Q and Q point. Of course, we had it, right? But I'm meaning here, because I'm over here in the cotangent bundle, I must have Q point is a function of P. P is a function of Q point. No, Q point is a function of P. Right, because I want this to be a function of P on the side. Right? Okay? Yes.
And so what is Peter's
Hmm?
unicorn? Peter's coupon? Oh, I'm gonna do that.
Let's review this. I'm making a Legendre transformation fiberwise. Okay? And I'm changing the function Q on the fiber Q point to the momentum function P. Right? This is the mapping. Right? And that's the same as, so, this is what I was alert, I pronounce your name wrong always, Ivan, right? Is that more or less right? If I change here, X, if I write here Q point, then you will be happy, I hope.
Yes.
Right? So, Q point is a function of P. Right? Yeah? Okay. Now, ready? I want to the Legendre, this thing will be called the Hamiltonian of P and Q. I'm just calling it that. Okay. So I make the transformation of the Lagrangian by the Legendre transformation, and I get what I'm calling the Hamiltonian of PQ. Here it is. But it's very hard to understand here in this notation because Q point is a function of P and so on. I mean, this is very, very implicit. Okay? Very, very implicit. Very abstract. Nobody is happy. Okay. Now. So this is the Lagrangian, this is the Legendre transformation, this is the Hamiltonian that results in it. Now, we will look at the partial derivative of H with respect to P and the partial derivative with respect to Q of H. Okay? This gives us a vector field, partial H, and I'm telling you the correct order here for physics, dDq plus partial H dDp. Okay? You agree? When you have a function, you have its derivatives and you get this vector field. Okay? The ODE of this vector field is Q point equals dH dQ And P point equals dH dP. Right? That is the ordinary, that's the ordinary differential equation of the vector. Do you agree? No, you don't like it.
I think it's DH.
No. You want me to make a sign change?
Not just a sign change. I think we should take with respect to P for Q dots.
Yeah, but you're just being formal and applying the physics in the back of your head. Don't do it. If you have a vector field, dH dq, partial dq, dH,
Yeah. Yeah, it's a vector field, but
huh?
right.
No, I think you're right.
I mean, this is a valid vector field.
No, I'm making a mistake. I made a mistake, and you're right. Who brought this? I think Deepak brought this. Thank you very much, because I made my first mistake. Okay. Okay. Well, okay, I hope I get this right now. Now, what I want to do, excuse me, I have to think, I'm very tired, by the way. Let's see here. What I want to do is I want to transform this Lagrangian over to this Hamiltonian field. So, what are the Lagrangian equations? The Lagrangian equation, I hope I did not erase. Oh dear. Can somebody dictate to me the Lagrangian equations? You know them by heart. So dl, I'll try to test by memory. D, plus or minus? This is the Lagrangian equation. Okay. Okay. Now we're getting to Iman's point. I'm men or I'm on? Men.
It's not distinction in matter.
You don't care. So, my name is Alain. In Kurdish, it means the great flag carrier. What about dH, for example, dH, dP? What's this equal to? Well, isn't this equal to Q point? Right? And now what about dH? This is the point I wanted to compute. I didn't compute it. Now I want to compute dH, dP, and dH, dQ. Why not? Okay. This is minus dL dQ. All right. And what's minus dL dQ? we have to use something here. And you guys dictate, oh, here it is.
This says at the center of the ball.
Pardon?
That's what you're looking for. P equals df. Df.
What are you pointing to?
The
Here.
left. Well, the other, the left half of the ball.
This is, oh, no, wait.
The left half. Left half of the ball.
No. Here's the LTQ. Here's the LTQ, right? Because that's equal, you even told me the minus sign. Yeah. The LTQ is equal to this thing here. So I'm going to, wait a minute, what's this thing here? The LDQ point. I'm getting very happy. Even Maria's almost happy. The LDQ point. She made me write Q point here, because she wasn't understanding this unless I write Q point, because we're making Legendre transformation with respect to Q point, right? What's the DLDQ point? It's the same as, in this notation here, DFDQ point. It's the same as P. That's the Legendre transformation using the Euler-Lagrange equation. Think of it, what we use. We use this equation and the Legendre transformation to write this thing equal to P point. Minus. Right? You get it again? Was that? I think
P point.
the derivative of P.
Oh, the difference. Okay.
This is a differential equation. Again, this is the Legendre equation. This tells us this guy here is equal to the derivative of this guy, so we need to know what this guy is. But this guy is the Legendre transformation guy, and the Legendre transformation guy is exactly P. P equals the LDQ point. Okay, that's what Maria made me write. Okay. So what we have here is, let me summarize it. Yeah? The Euler-Lagrange equations on the tangent bundle in the coordinates Q point are transformed by Legendre to the Hamiltonian equations which have this form, and that's what Ayman was looking for. I don't know what you'd like to write first. DH would be Q equals minus. What do you like to write first, Q or P? I think Q first. P point. Oh, P. Oh. We write the variables in the order that they are. So Q point equals DHDP. And P point equals minus DHDQ. You got it? It might still be worth making a slow remark what we did. We had the Lagrangian equations written here for minimizing the energy functional is equivalent to the solution of this ODE. We transform this ODE by the Legendre transformation to the cotangent bundle, which has coordinates Q and P, and obtain the Hamiltonian equation. Now, that's certainly an improvement. Yeah, that's big time improvement. Now, fortunately, I have time to explain what that means. Okay? So this is an embedding of Lagrangian mechanics in Hamiltonian mechanics. By the way, if you do it again, Legendre of Legendre is the identity. So this is really nice. It's sort of an involution. It goes from tangent bundle to cotangent bundle back to the tangent bundle. So it's a perfect thing. Okay. So the meaning of this. Now we're going to have some fun. Watch. Here is the cotangent bundle. Here is the manifold. Okay. Here is, well, let's take this fiber here over a point, I don't care, x. So no coordinates, just x. And let's take a tangent vector here, which we call tau at the point. Now we have to be careful. This is the fiber over x, and this is the point which is a differential form at the point x. So this is the tangent vector at the point alpha of x. You get it? So x is a point in the manifold. This is a projection. You take a tangent vector upstairs. It's someplace in that fiber. The point we're taking is, we're calling alpha of x. Okay? Now you do the following amazing thing. You take that vector there and you push it down. Okay? So everybody knows you can push down a tangent vector. Right? And you get a tangent vector down here. Right? So just for fun, let me write this. This is in the tangent space at x. What's the fiber? Those are all the one forms on that tangent vector space, right? Right?
So pi star is a projection to the manifold from
Yeah.
the cotangent bundle.
No! I'm glad you asked because it is confusing. If I take a tangent vector on a manifold and a mapping, it maps it to a tangent vector on the image manifold. Right? Push forward.
Okay, so pi here is not the pi of
Pi is the mapping from the cotangent bundle to the manifold.
and pi star.
Pi star, oh, I see, it's a question of stars. It's the push forward of that tangent vector.
Okay.
I think it's worth discussing. If you have n to m, and you have a point here x, and you have, this is a mapping phi, and phi takes x to phi of x. Yeah. Then phi star maps the tangent space at x of n to the tangent space of phi of x at n. Just pi star. Okay? You push forward. It's called the differential of the map. Okay? Okay? Yeah, look where it is. It's at the tangent space of n. Look where alpha is. It's a one form on the tangent space of n. So, what I do is, I just apply alpha of x to this thing. You got it? You should be excited because that was a completely canonical construction. Right? Given anything on the tangent space of the cotangent bundle, right? You have a way of evaluating it and getting a one form. I'm evaluating, I'm getting a number associated to that thing. This is what is called lambda of tau. And it's not a Lagrangian multiplier. Yes.
What was alpha? Alpha was any.
Any one form, any point in the fiber of the cotangent bundle over the point x.
Right, but I still don't see why it's canonical. Because,
I haven't used anything.
okay, so it's that. Okay, so the
Let's try this. You give me a point on the base. Okay? And I say, okay, I'm going to look at tangent vectors above that point. Right? Or not even better, I'm going to look at tangent vectors somewhere upstairs, and if it's somewhere upstairs, it's above some point. I'm going to call that point x. Maybe that was the better, if I'd done it that way, you would have been confused. So I start upstairs with a tangent vector someplace. It's over a point x, and it's at a point alpha of x, which is a one form. And now I push it down to the, now I get a tangent vector on the base, and I apply the one form to it. I get a number. This is a number given by God. Well, the word canonical comes from the Bible. I mean, it's a little bit Christian, but I mean, maybe we shouldn't have Christianity playing a role. But
I'm sorry. So, we pick alpha x. How is that canonical?
yeah, psychologically, I gave a bad lecture just now. Let's start again. Take a point in the cotangent bundle. Any point. Take a tangent vector at that point. Any tangent vector.
Okay.
That point lies over a unique point in the base. Call that x. That point of the cotangent bundle is a one form, is in that fiber, so it's a one form on that tangent space. So I push down the tangent vector and I apply the one form. Right? You don't need any politician for this. It's given to you by God. I don't go to church, but it doesn't matter. God gave us it. You agree, it's canonical. Okay? It's a canonical one form. It has a name in classical mechanics. It's called the Liouville. Liouville is a French mathematician of the late 18th, 19th and early 20th century. Liouville. It's called the Liouville form of this thing. Okay? Canonical form. Okay? That should make us incredibly happy that there is a canonical one form on the cotangent bundle and there is nothing canonical on the tangent bundle. Let me say it for the record, there is nothing canonical on the tangent bundle, but there is something canonical on the cotangent bundle. And therefore we need a way of going from the tangent bundle to the cotangent bundle to use that, and the way is called Legendre. Okay? Isn't that reasonable? Okay, let's compute lambda. Okay? I'm going to tell you the answer and you can have fun computing, it's trivial. So lambda in coordinates. QP. Now what does it mean Q and what does it mean P now in coordinates? Okay? Okay, so let's say Q is the base coordinate is Q1 through Qn. There's absolutely no question of what that means, right? Right? P is a one form, right? P is a point in the cotangent bundle, so therefore it is a one form. So P equals, as a one form, is equal to sum Pi dQi. You agree? Because dQi, dQ1 through dQn is a basis, is a frame for the cotangent bundle. And so P is a linear combination with functions of that frame. Okay. So P is equal to P1 to Pn. Okay? Okay? Now, if you do the computation, lambda is equal well, lambda, what is lambda equal to if you have a vector? Where the heck is the cotangent bundle? Here, if you have a vector which is in the fiber direction, it gets killed by this projection. So lambda has to be trivial on this vector. It gets projected and gets evaluated. So lambda has to be trivial in the fiber direction. That gives you a hint what lambda has to be, right? It has to be trivial in the fiber direction because this projection kills it. So that has to be in the base. And in fact, if lambda is equal to P dq. Obviously, it's only going to involve the base variable because we projected and did something in the base. And if you compute it out, it's P dq. You understand what that means? That means these functions, I mean, I'll just write it. P1, dq1, and so on. Okay? This is the Liouville form. And the key structure, there's a canonical structure, but just as canonical is the associated symplectic form. Is what I call omega standard is minus d lambda, which is equal to dq dq. There's a sign here that for some reason. I'm sorry, but there's a sign. What?
I'm just looking at the representation. So isn't lambda equal to p in that case?
Isn't lambda equal to what?
P. Because p is just the sum of p.
Yeah, you're absolutely, I understand the confusion. Well, let me say it all again. I'm sorry, I just had to repeat. Okay, you have coordinates in the base. That's Q1 through Qn. You have coordinates in the fiber direction. Well, what are those coordinates? Fiber is a form. So it's a linear combination of the dq's. The coefficients are varying, they're functions. So those coefficients are the coordinates of the form. So the coordinates on the product is the base coordinate and the fiber coordinate. Fiber coordinate is P1 through Pn, the base coordinate is Q1 through Qn. And where is your problem?
It's just an observation. It's by the fact that what we wrote on the blackboard, they're just the same, right? So lambda is P1 dq1 plus P2 dq2. And then P is just P1 dq1 plus P2 dq2, which means they're equal. It shouldn't, right?
I'm not yet sure what you're asking. Can you ask it in some other way?
Yeah, right. So you see that you say P is the sum of all the dI's, dQi's, correct?
Okay. So let me even write it this way. dq1 through dqn is a frame of the cotangent bundle. So that means if you have a local section, which this is, it's a linear combination of the frame.
And you write lambda in exactly the same way. So it's p1 dq1 plus other stuff plus pn dqn. I think
That's right.
the confusion is that why is that not the same thing as p?
Well, because these are functions, the pi are functions, I don't know. The pi are functions, of course, where are the pi's functions?
And then the lambda.
Can we go on how we found the Liouville form again? Maybe just to clarify things. So Liouville form.
Yeah.
So if we studied in the tangent, in the bundle direction, what did you mean by that?
The fiber direction. It is 0.
Makes sense.
Huh?
Because it's canonical on that.
It's 0 because it's given by the projection. So,
Is there some sort of sloppy notation?
hmm?
Is there some sloppy notation that's
This-
causing?
I'm not sure this is sloppy notation. It's just confusing for a moment.
So lambda is a function? Where does lambda be? Is it?
Lambda, well, you know what lambda is. I defined it. Lambda is a one form on the cotangent bundle space. Right? And as soon as I have coordinates, I can try to write it in coordinates. Right? And therefore, so what are these PIs?
Well, it makes sense to be the same then. I mean, P
What?
is also one form on the tangent bundle space, right?
Because it is trivial and one is higher, so it's a dynamic sense. They are in different space, but it is trivial on the higher, so it can make sense.
So P is one form on the.
So more or less it is just depending on the points.
Pardon me, the P's are not constant.
Now it's Q.
So P is on the manifold, the other is on
Okay. What does this, the question is maybe what this notation means even. I think this is what he was suggesting. Huh? It looks okay to me.
Yeah.
If you apply, look, if you apply this thing to a vector partial of, with respect to qj, you get pj. Right? You get pj, but don't forget it. Pj is depending on which point you are in the fiber. That's maybe the confusing, right? Those are the linear coordinates of the fiber in some sense, pj. This statement here is this. If I would evaluate this just at a point, this is the basis of the fiber of that point, and these are the linear functions on that point. Those are the coordinates of the point in that basis. I don't think it's confusing. Okay. Why don't you like this?
Why is the notation the same then?
It's the same symbols of the little different spaces.
Yeah, there are two different things, but the same notation. You're right about that. This is writing a one form in a basis. Okay? This is writing a one form in a basis. This is a one form on the manifold. Okay? I mean,
Can I say, it's one form on the manifold also written in the basis.
I mean, it's so close to being the same thing, it almost doesn't matter. But I mean, okay?
The PIs are numbers, right?
The PIs are here numbers, and the PIs here are functions. I mean, but it's, okay? And since there are functions, I can take the differential of that form.
Okay, I see.
Okay? So everything here, the Liouville form this is Liouville form. And this is the standard symplectic form. Okay? And physics people will not write wedge. They will forget the wedge and write just dq dp. Okay? Now, so definition. A two form on a manifold a two form, call it omega, a manifold is said to be symplectic if it's closed, and non-degenerate. Everybody here understands closed. We should understand what it means non-degenerate. Okay. So omega maps tangent bundle across the tangent bundle to a function, to real numbers, is non-degenerate whenever omega v point is 0, implies that v is 0. I've been a little sloppy here, but you understand that? So you have experience with bilinear forms. You put a vector in the first argument, you get a linear function. If this is 0 as a linear function, the only way that can happen is if v is 0. Okay? I like to write Tm perp with respect to omega is 0. set of vectors which is orthogonal to everything is the trivial vector. Okay? Now this does not mean that there are vectors, that there are no vectors of length 0. You know this, with the things on the boundary of the light cone, of course, are norm 0. Right? But they're not orthogonal to everything. So that's what this is. So a fact that you can easily check is omega standard is symplectic. On the cotangent one. Okay? And you can check it just in coordinates here because it's just this thing. Okay? Now, the last remark and then we can quit for today. I'm sorry, you're probably very tired. This is a very beautiful remark. It's called Hamiltonian mechanics. Hamilton's idea. You start with the Hamiltonian. He didn't call it a Hamiltonian, but you start with the Hamiltonian, which is any function, and you take d of this. And you say that's a one form. That's a one form, right? But if you have the standard symplectic structure, that's a one form. I can contract this. It must be equal to the contraction. Here's an incredible idea. With some vector field. I don't know your notation from. Do you use that as contraction? Let me just write it out. It's this. You just put it in the first argument and you get a one form. And since this thing is non-degenerate, that's a really well-defined guy, right? Okay, so this is a mapping from functions to one forms to vector fields. Okay? From one forms, functions to vector fields. Suppose you have coordinates, like we have here for the whole lecture, Q and P. We will see next time when I start introducing you to the symplectic methods here, what this thing is. This thing is, well, now I'm going to make sure I get it right. What should I do first? I'm sorry. Did I get it right? I hope I get this vector field over here. Check with me on that. The vector field over here is right? So the integral curve of this vector field would be Q point equals plus or minus dp. Minus dp and P point equals dq. Okay. So you see that in fact our vector field that we have here is a Hamiltonian field for some Hamiltonian function on, well, we know what it is. So this is the Hamiltonian mechanics picture. Okay, I know you're very tired of this tough day. Okay? So I don't think I need to repeat it, but I'm going to just because we have a little bit of time. We start with, let's not even write, let's just think together. We start with the notion of a geodesic defined by a connection. Very intuitive, but the most intuitive thing is a geodesic defined by distance or length. We realize that in order to find the critical points of the length function, it's the same thing if you use arc length or curve length as parameter to find the critical points of the energy function, of the action. To find critical points of the action, you do calculus. You take the derivative of the action, right? With all perturbations of all curves nearby with the right endpoints. You do that and you find the Lagrangian equations. That is in fact a completely general thing. You have the integral of some Lagrangian and so on, you find the Lagrangian equations. Okay. That is something on the tangent bundle. The cotangent bundle, as it turns out, is much better than the tangent bundle because it has, God gave it structure. So we're hoping to use the structure from God somehow with these Hamiltonian equations. So we take the Lagrangian, transform it by the Legendre transformation to the Hamiltonian equations, and we find that we have these wonderful Hamiltonian equations. Then we see that on the cotangent bundle, this guy, lambda, is, although it's a little bit confusing, that's the guy lambda, and d of this lambda is the right symplectic form to discuss. Once you have a symplectic form, everything's canonical now. Once you have a symplectic form and a function, you take d of the function, and that's a one form, and that's equal to a contraction of a unique field of this two form. This is a mapping from functions to fields. Every physicist knows this. This is a mapping from functions to fields. Some physicists will do this and say that's an operator as a vector field, and they will write this Poisson bracket, as you know. This is a mapping from functions to vector fields, and this mapping looks like this. Now what do you know? The exact thing that we got by Lagrangian, like the Legendre transformation, is exactly a Hamiltonian system in this way. Okay? And therefore we have a much better place to look at this whole thing, namely the Hamiltonian mechanics of the cotangent. Okay? I will spend all next week talking about symplectic geometry and how this plays a role in everything here that we've seen. Okay? It's also a lot of fun, symplectic geometry. Okay, thanks for your patience today.